sleep and study. Don't forget to subscribe.
Let's move on to supermassive black holes. We remember that the observed black holes are divided into two main classes. These are stellar mass black holes and supermassive black holes. This graph shows this schematically. The yellow peak corresponds to stellar masses, more or less. And the blue peak corresponds to supermassive black holes. Some known sources are marked, in particular black holes for which masses have been measured from gravitational wave data. There's one black hole of more or less intermediate mass in the galaxy, Sagittarius A star, one of the most known supermassive black holes. There's a caveat to be made here, which I'll come back to. We're actually talking about known objects at the moment, and there are two families and a void between them. In fact, when we talk about black holes in the universe in general, this void is very densely packed, and in fact they say there should be more small objects with masses from a few hundred masses of the Sun to about a few 100,000 masses of the Sun compared to the most massive black holes. But for reasons we will discuss later, so far this large population of objects has not been detected. But all such scenario population stratophysical considerations suggest that such a population must exist. Here's a rough outline of the lecture we're going to talk about, some general introduction. We will talk a little bit more about Sagittarius A star, general properties of supermassive black holes, and then we'll talk about mass measurement. Naturally, there are a lot of reviews on this topic. They're updated pretty quickly. And it's such a hot topic where there are constantly new results all the time from the old reviews. 15 years is an old one, 14 even. I kept one. I find it so informative. It's just that at some point people stopped mentioning that there were alternatives to supermassive black holes. And in that sense, it's significant that at some point these alternatives were discussed. And in that sense, there are considerations that say, why can we say exactly that there is no such alternative to supermassive black holes today? There are very tight constraints on all the other scenarios that were once discussed. Once upon a time is back in the 80s, let's say. Anyway, not that long ago. But as of today, maybe some of them are applicable in individual cases, but not to explain the whole population as a whole. Okay, a little bit of history. The very idea that there may be supermassive black holes in the centers of galaxies appeared in the 60s, and it was connected primarily with the identification of quasars, with the realization that we are dealing with very powerful and very compact sources. Let me remind you that compactness was established by variability, and the variability of the first quasar 3C273 was demonstrated by the Geist staff just now. After it became necessary to explain compact, very powerful sources in the central parts of galaxies, there were several ideas, which then went on to be debated for a couple decades. Among these ideas, there were such as supermassive stars, for example, stable by rotation. There was the word spinors. There were discussions about very powerful star formation in the center of galaxies, which could explain a number of phenomena associated with active galactic nuclei. But the idea of supermassive black holes, accreting supermassive black holes, appeared. More or less simultaneously and independently, the ideas were expressed by Salpeter, Zeldovich, Novikov, and Lynden-Bell. In the pictures, you see Salpeter and Zeldovich. Today, we can say that, with very few exceptions, all galaxies that have a significant bulge, and that automatically means all early type galaxies, that is, all electric galaxies, must have a supermassive black hole at their center. Supermassive black holes have been observed in a number of galaxies. First of all, of course, we are talking about the manifestation of galactic nucleus activity. And supermassive black holes have been observed in distant galaxies. What is important, we will discuss this further with you in the next lecture. There's a problem in that black holes that have masses of the hundreds of millions of solar masses already exist in the first few 100 million years of the existence of our universe. The activity of galactic nuclei is not some rare phenomenon. A few percent of galactic nuclei show such activity. And we think that more or less all supermassive black holes at the centers of galaxies have gone through an active stage at some point in their lives. And now, if we have a catalog of quasars, a catalog of active galactic nuclei, we can say with certainty that there are supermassive black holes there. Modern catalogs have a very large number of sources. The masses are already harder to measure. And basically, but these are not hard limits. The masses of supermassive black holes are generally in the range of 1 million to a few billion solar masses. But you and I will discuss black holes of intermediate masses separately in this lecture, which have also been discovered in increasing numbers in recent years. Finally, the most reliable object in this sense is probably the black hole in the center of our galaxy. It's the best studied to date. It's the best studied simply because it's close. Of course, it would be easier to study if it had a larger mass, not a few million, but say a few billion solar masses. But in our galaxy, such a massive black hole isn't allowed, billions of solar masses, because our bulge is small. What can we do? We can observe the neighborhood of supermassive black holes in the center of the galaxy with ever-increasing precision and detail. Specifically, we can observe the motion of stars in the central region. And there's a known star called S02, which has an orbital period of just over 15 years. Accordingly, during the period of observation since the early 90s, it has already made more than one complete revolution around the central black hole. Then we discovered another star. This one began to be studied in the early 1990s simply because it's very bright, it's easier to study. But studying stellar dynamics in particular helps us to measure the mass of the central compact object. Stars are observed in the near IR because in general the center of the galaxy is covered with dust. In the optics it is not very visible in the classical optical or ultraviolet. But dust is also transparent, except for infrared for X-rays, and also for this range. So there's a large set of observational data, and it's growing to observe the region of the center of the galaxy in X-rays. It's not just for the supermassive black hole. There's a lot of interesting objects, double systems, and that's why you're seeing such a large area. But in this case, the field, as you can see, is 17 by 17 angular minutes, which is quite small. And this corresponds to about 40 by 40 parsec. That is really such a central area. An arrow indicates the position of Sagittarius A star. And once again, I repeat, this is all only X-ray data. The colors are artificial. That's how they are coded. It is described here. Accordingly, there is a lot of diffuse X-ray emission and a huge number of point sources. Chandra, as you remember, has excellent angular resolution for the X-ray range and can build such detailed maps. Well, you can zoom in on all of that and see more than an order of magnitude more compact neighborhood of the center of the galaxy. The Sagittarius A star source itself is marked with a cross. Here it is in the center of the left frame. Here, and there are all sorts of bright sources around it, some of which are associated with binary systems and some are not. So the stellar dynamics have been observed for over 25 years. And this allows us to accurately measure the mass of the black hole, which is about 4 million solar masses. Well, there are stars even closer than the C02 star mentioned above. There's a star called C62. It has an orbital period of 10 years, that is 1.5 times less, but the star is less massive, 2 solar masses, so it has not been observed so long ago. And this year there's been some detailed observations of it. In the picture, respectively, the red ellipse, the smallest and most elongated, it has a very large eccentricity, corresponds to the star C62. Observing stars in the neighborhood of a black hole in particular, by the way, helps to test the effects of the general theory of relativity, which I guess is what I'm talking about. I'll probably say a few more words about Not to say that these are any very severe limitations compared to pulsar data or to data in the solar system, but nevertheless, the observations are important because it's a different object. So the idea is that we can use Sagittarius A star to make even more detailed and really very detailed constraints on models of gravitational theory, to test all sorts of black hole theories that are in general relativity. For this, I'm describing the right-hand picture. For this, we need new observations, and in particular, everyone, of course, is waiting. The Event Horizon Telescope will be able to tell us something about the center of our galaxy. Unfortunately, it probably won't, but nevertheless, we're waiting for the results to show us. It won't be able to because we'll be coming back to it. The orbital period in the last stable orbit around Sagittarius A star is quite short, half an hour. And that corresponds to the mode in which the picture is blurred. And in the case of the black hole in M87, there we are dealing with a much more massive black hole, and so the orbital period is much larger. And so the Event Horizon Telescope is the whole Earth as a telescope, a platform full of telescopes, and it matters how fast the Earth is spinning. The Earth spins slowly, that is compared to half an hour time, in which all the telescopes included in the Event Horizon Telescope conduct their observations, is quite long. And the picture for M87 doesn't blur much, but for Sagittarius A star, it blurs a lot. In addition, the interstellar medium is probably interfering with the ability to observe at the wavelengths at which the observations were made. And so accordingly, looking into the distant future, the problem is solved by building systems of space telescopes in the radio band in the millimeter range. But these should be systems exclusively space telescopes, that is, without the use of ground stations. And such plans will obviously not be realized soon. But when it will be realized, what do we have? We have data on stars that pretty well constrain the rotational parameters of our black hole. Accurate data on pulsars can be added to that. And then if we add the shadow data, then the quadrupole momentum can be determined quite well, which is important. And now, respectively, about the left picture. On the left picture, on the horizontal axis, is the distance to black holes, and on the vertical axis is the angular size on the sky. Accordingly, the angular size in the sky depends on the combination of the size of the horizon, that is, the mass of the black hole and the distance to it. And three objects are distinguished. First of all, Sagittarius A star stands out. It's the largest hole in the sky. And M87. We will mention very soon the black hole in the center of M31, but for it the mass estimates are constantly being refined, I would say changed a little bit. There used to be mass estimates that made it the largest object in the sky from this point of view. But lately things have been settling on the fact that this black hole is a little bit smaller. It's still more massive than ours, but not 100 times, say, more massive, or even 30 times more massive, but less than 10 times more massive, apparently. And so the much greater distance makes its angular size small, but it's still such a number 3 target in the sky. It's good to remember that as well. And so you see this limit right here. That's an observation at 1 millimeter. And so the effective size of the interferometer is the diameter of the Earth. If we want to go deeper and we want to study a lot of objects, then we need to go a little bit shorter wavelengths. But the most important thing is to make the size of the system much larger. Here we go. 300,000 kilometers from the moon, yes, but let's say the radio astron didn't work at 0.4 millimeters, it worked on much longer wavelengths. And so even though the record for angular resolution is held by the radio astron, it can't go that far. Well, and the long wavelengths he was working on are preventing us from seeing the very center of the galaxy. Let's go back to the center of our galaxy. So we have a black hole there with a mass of 4 million solar masses. and it's so relatively quiet right now. But we know that it wasn't like that in the past and on different time scales. So if we're talking about hundreds of years, then the important constraints come from the X-ray data. In this case, we are talking about data from the integral satellite, which has very much observed a black hole in the center of the galaxy. And this is what has been observed. This is such a very central region. Sagittarius A star and Sagittarius B2 is a molecular cloud. And molecular clouds are not normally such powerful sources of hard X-rays. And that's what the integral is receiving. But in this case, it is. And the idea is that this is a kind of light echo. But the signal is not reflected, but re-radiated. So a few hundred years ago, the central black hole experienced a massive X-ray burst, or let's say a period of activity. So its luminosity was much higher. And this radiation is slowly pumping up the molecular clouds in the neighborhood of the black hole. And accordingly, we can determine from the delay of this echo how many years ago there was activity. Now we're seeing X-rays from several other clouds around it. And it's being studied in such detail. Well, if you're interested, you can check out this paper from 2016. There's more detailed data on the study of this fluorescence echo. There's a lot of the data from the integral on the center of the galaxy, as I said. Well, this is a pretty big scale right here. This is, as you can see, a couple degrees by a couple degrees square. And along with the weak signal from Sagittarius A, we see more powerful sources. They're mostly twin systems. The center of the galaxy is observed in a harder band with TV telescopes, gamma-ray ground-based telescopes. The source is visible, but these instruments don't have enough resolution to make a rigorous and unambiguous association, the observed source to the central black hole. But all indications are that it is. That the addition, the mixing of radiation from other sources is insignificant. So, although we say that the black dry at the center of our galaxy is so quiet, so peaceful, nevertheless, quite often there are outbursts there. You don't see them super often just because telescopes aren't looking at the center of the galaxy all the time. But you can tell the rate of the bursts. It's quite large. And if in a quiet state the luminosity is about the same as the sun, then in outburst the luminosity can increase by tens, sometimes hundreds of times. And the typical long outbursts are anything up to about an hour long. Here's one example of a burst from X-ray data. Different satellites are constantly monitoring, so they're constantly monitoring the center of the galaxy. Here, in particular, there's a lot of data from the Swift satellite, and you can see flares that are quite powerful. But probably the most interesting is the data from Chandra and XMM. These are the more powerful observatories, and therefore they can collect a lot of photons very well. We'll see on the next slide the number of photons that are registered and therefore build up good spectra. But you can see that there are a lot of Chandra and XMM observations, and so sometimes they give very bright flashes. Here are the results of more than a decade of monitoring. Accordingly, on the vertical axis is plotted the flux in counts per second. That is, 2 is 100 photons per second, 3, respectively, thousands of photons per second. That's a lot. Given that Chandra exposures can be many thousands of seconds, sometimes there are large exposures of 1 million seconds. So you get a large number of photons, and you can study the variability in detail on a small scale and build up detailed spectra. Well, in terms of duration, the bursts sometimes last longer than an hour. And so there's really quite a lot of energy released in these flares. Recently, less than a year ago, there was a paper on the brightest known flares. And these flares appear to be associated with some kind of changes in the accretion rate, in the behavior of the central black hole in general. The processing of the observational data shows that there's an increase in the number of the brightest flares. These are the brightest flares, have a very high count rate, and you can see here's Sagittarius A and here's the magnetar, which is not far away from it, and you can see how bright Sagittarius A becomes during a flash. And so when it's calm, it's hardly visible here. flashes are also observed in the infrared range. Here, accordingly, can be used ground-based instruments. And in general, Sagittarius A star has a maximum in the spectrum, as we'll see in the future. The maximum of the spectral distribution falls in the infrared. And so infrared observations there are very important in that sense. Accordingly, again, there's been a record recently for a powerful infrared flare. The flux was at least twice as high than previous record-breaking flashes. So accordingly, it was possible to, it's a long observing session. Accordingly, people monitored how the light curve behaves during this flare. Well, here it is, this very spectrum. It shows the spectrum in the calm state and in the flare state. The maximum, as you can see, is in the infrared. And some of the spectral components are highlighted, and therefore the emission mechanisms are written down. The emission mechanisms, as you can see, are mostly non-thermal. As for the size, but here let's first, so that we have something to compare it to. If the mass of a black hole is 4 million solar masses, then accordingly the Schwarzschild radius is about 12 million kilometers. This is a little less than 1/10 of an astronomical unit, and for quite some time now, that is a few years ago, 15 years ago, thanks to ultra-long baseline interferometry, the size was limited to 1 astronomical unit for actually a compact radio source. But since then, there's been a lot of progress, and it's gone well under these 10 Schwarzschild radii. Here, for example, the result from 2 years ago. An article from 2 years ago. Again, the observations, they are standard at wavelengths of 0.3 millimeters. In this paper, it was shown that it can seem that the radiation is asymmetric. That is, you can see some structure. It is not possible to get pictures of this structure, not that detailed images, but at least the properties of the image are inconsistent with an unresolved structureless source. And accordingly, the size of the structure corresponds to about 3 Schwarzschild radii. This is small, since 3 Schwarzschild radii is the last stable orbit. What else can we see? During the flares, we were able to see a shift of the centroid of the image. Accordingly, we can start with the picture A. Red and blue are the shift respectively at the 2 coordinates during the flare. And the displacement is well described in this part here in panel C. The observational data is described by theoretical curves. It's not a best fit, it's a theoretical model consistent with a circular orbit on 7RG in this case for a non-rotating black hole. All in all, it works out pretty well. There's a real sense that these different observations were obtained at different stages of the rotation of the radiating region around the central black hole and the distance. Again, on the order of the last stable orbit. But here you can capture this in a slightly different way. I'll zoom in on this figure. So on the horizontal axis, the size, and on the vertical axis is the orbital period. And for several of the flashes, there was a movement with different periodicities. And accordingly, this corresponds to different positions in the orbit. And the red line is the last stable orbit for a non-rotating black hole. We know the rotation parameter actually for our central black hole, but it's quite small, and so the corrections here are small. And for the corresponding mass, 14 million masses of the sun, you can see that the observational data fits quite well on these lines. So we can say that we're looking at the rotation of some kind of radiating cluster around the central black hole. But it's interesting to study the neighborhood of the central black hole on different scales, not just on the smallest scale. And last year, an interesting result was presented. It was obtained on ALMA. It involved the observation of a debris disk at distances of about 10 Schwarzschild radii. But there's this big picture here, a big picture of the structures around the central black hole. The innermost region is zoomed out. accordingly the radius of gravitational capture for accretion. And it shows the orbit of the G2 star that we talked about at the beginning, a piece of the orbit of the known object G2. And it's on this scale, this blue ellipse here, that ALMA detected the thermal emission. And it's clear that it's a disk. The idea is that the observation was made in the center line. And it is possible, respectively, to distinguish the blue and red components of this line. And so, due to the Doppler effect, we can see the parts of the disk that are moving towards us and away from us. Here they are shown. This part is moving towards us. This part of the disk is moving away from us. And so, accordingly, it's possible to directly study the properties and behavior of matter on scales of about 10,000 Schwarzschild radii. And what we're observing, respectively, a disk with a characteristic temperature of 10,000 kelvins. What else do we have interesting in the center of the galaxy? Thanks to the work of the Fermi Gamma Ray Space Observatory, very interesting structures, the so-called Fermi bubbles, have been identified. Everybody's probably seen this picture. The data that there are some structures in the central part of the galaxy, perpendicular to the galactic disk, appeared long ago. It was connected, if you can consider it here, with WMAP data and with RASADA data. That is, something like this was being drawn on the maps, but what was needed was good gamma observations to identify these structures properly. The idea is that 1 million to 10 million years ago, our black core was much more active, so it really was a weak active galactic nucleus. And the accretion rate was higher, the luminosity was higher, and there was an outflow of matter from the central region. Accordingly, it was easier for matter to move perpendicular to the galactic disk, to move into the low density, low pressure region. And because of this, these bubbles were blown out thanks to the activity of the central black hole. In recent years, just about a year ago, in fact, there's been a paper where people are trying to identify additional structures associated with bubbles, like this. How do you say chimneys? Accordingly, from the center of the galaxy, the Fermi bubbles are oriented like this, in the vertical perpendicular to the galaxy density. Here, respectively, the base of the Fermi bubbles are shown, and structures were found like this, elongated towards the Fermi bubbles, which are called, appropriately enough, chimneys. Okay, the center of our galaxy is more or less figured out. At the center of the Andromeda Nebula, there's a central compact object. A central compact object, a central black hole, it has a slightly higher luminosity than ours. Typically, it's several hundred times higher. And the mass is estimated, well, there used to be estimates more like as high as 200 million solar masses. But today's estimates are a little bit lower. The mass 10 years ago, as you can see, when the mass estimate was large, then therefore it would appear that the Bondi radius, it characterizes, as you remember, at what distance a compact object can capture the surrounding gas. And so therefore here M31 comes first. So it may be possible to see some structures in the center of the nearest large galaxy. Well, here, the main hopes for the observation of structures in the center are still associated with the Event Horizon telescope to date. Radioastron gave many important results related to active nuclei. But for the nuclei themselves, there are high hopes for the Event Horizon telescope, and the ALBA telescope system has given a lot of results. Accordingly, we all remember the results on the M8080 galaxy. On the galaxy M87 of the Virgo constellation, the so-called black hole picture, there's been a lot of discussion about it, so I probably won't repeat myself here. What's essential is that by taking images like this, allows us to more accurately determine the parameters of the central black hole, particularly its mass, and thus test other methods of mass estimation. Well, and in the case of M87, by the way, with a factor of 2 or so, the methods worked very well. Yes, there's one more thing I didn't say about M31, just like our black hole. The black hole at the center of the Andromeda Nebula goes from brighter to fainter. And so there are changes in the accretion flow there as well, so which affects the X-ray luminosity. But until the year 2006, this cross here, this is the central black hole. We see a very faint object here, and after 2006, there was a pretty powerful flare. There are hints of Fermi bubbles in the Andromeda Nebula as well, and that would be logical, shall we say. It's logical to expect that there's a black hole there, a more massive black hole with variable activity. Some tens of millions of years ago, it could be in a more active phase and also blow such bubbles that we can now observe now in the gamma ray band as some rudiments. Okay, so if we're talking about active galactic nuclei in general, there are many different ones. And there are some pretty intricate, I would say, classifications. So there's a very rich phenomenology. There's a lot of beautiful words. Linus, blazes, Seyfert galaxies. We're not going to go into all this phenomenology in detail. It's not our task. It's more interesting to talk about the central objects themselves, but we'll devote a little bit of time. But we'll devote a little time to that. The spectrum of the active galactic nucleus consists of several components. That is, first, of course, if it is an active nucleus, there is a powerful accretion disk, and then there is the disk emission. This is very similar to what you saw when we looked at the spectra of accreting black holes in double systems. There's a spectrum of the disk. There may be a corona above the disk with hot electrons, and so there's a compotonization of the radiation, and it grows a hard tail like this. You remember that some of the radiation from the corona falls back onto the disk, is reflected. The green dashed line shows this component, and it is in the reflected component. There's a strong line of iron. Accordingly, the strong iron line is at 64 kiloelectron volts. And naturally, if there are jets, they give a strong contribution. It's usually such a two-peak pattern. Well, here's the dotted line shows one variant of the jets, and the brown solid line shows the other variant of a jet. And if we're talking about active galactic nuclei without powerful jets, well, at least we don't have jet emission in our observations. It may still depend on the orientation in some cases. So therefore, the bold black line here roughly describes this. There is little radio emission because there is no jets. Radio is mostly related to jets after all, but there is quite powerful X-rays and quite powerful optical radiation. There's optical and ultraviolet, but there's also some infrared radiation, of course, is naturally present. There's a lot of X-ray data on active galactic nuclei. It's easy enough to identify them there. And they show the redshift distribution of this sort of averaged luminosity function for galaxies, for active nuclei with different luminosities. That is, it is all normalized by the cubic megaparsec. Accordingly, it can be seen that for the most powerful active galactic nuclei have a maximum of Z2. That is, there were no powerful active galactic nuclei in the very distant past universe. Well, there weren't many, let's put it that way. You see, there's a signal here all the way up to a 5. And now we know that there are slightly more distant active galactic nuclei than Z5. But there's a clear statistically significant decline towards higher redshifts. The number of these objects is slowly increasing. And after about Z2, it starts to fall. For slightly fainter active galaxy nuclei, we see a similar pattern, but the decline is later. Even fainter ones are also similar, and the decline is later. And for the faintest active galactic nuclei, the decline is quite early, I would say, in our epoch after just a few decades. That is, such an epoch of weak active galactic nuclei in this sense has passed. And it's not by chance that in our rather large neighborhood, generally speaking, we don't see active quasars. Accordingly, the spectra of quasars, well, they generally speaking differ from each other, but we can talk about a typical spectrum Accordingly, there is a powerful radio emission. We say here we have a picture of a radio loud quasar. There's a power tail going into the radio emission. And accordingly, there's a thermal part associated with the accretion disk. And in the case of massive black holes, here the maximum falls in the ultraviolet optical region, unlike stellar mass black holes where the maximum falls in the X-ray region. Well, here's kind of an averaged schematic spectrum for 3C273 and similar quasars. If we have powerful jets, then there's a second maximum at higher energies. And therefore, the energy here you see is deposited in electron volts, so it's fantastic energy. Accordingly, we see gamma radiation associated with the jets of such objects. The best way to register the hard radiation of the jets is if the jets are directed directly at us. If we're looking perpendicular to the jets, we'll see radio emission that's mostly associated with the area where the jet is crashing into the surrounding intergalactic medium. And if we're looking along the jet, we'll see in particular very hard gamma rays, and such objects are called BL Lacertae type objects, BL Lacertae, and then there's the more common blazars. Blazars are objects that are active galactic nuclei, and they're jetted directly at us, and so the radiation is stretched out to very hard gamma rays. A lot of data on blazars came out when the Fermi satellite was launched. And Fermi sees, well, let me show you the third catalog. Now there's a fourth catalog. A year ago, there was a corresponding paper on active galactic nuclei in the fourth Fermi catalog. Accordingly, you can see about 2,000 objects of different types there. And here you can see that the blue one shows Lacertidae, and there are a lot of them. So if the jet is pointed directly at us, we see gamma radiation, and that's interesting. First of all, as in itself, it explores all sorts of interesting physics associated with active galactic nuclei, and it's interesting as a tool for cosmological research. Here's why. Blazars can be far away, really far away. Z is equal to several. So the light takes, say, 10 billion years to reach us. And these hard photons, they have a lot of energy. If they interact with other photons on the way, they produce electron-positron pairs. There are always background photons associated, in this case, not with the CMB, because CMB photons have low energy, not related to the CMBR, but to the background optical ultraviolet radiation. But they're mostly associated with the same blazars and the stars. Accordingly, what would happen if some of the gamma rays in the blazar radiation would be diverged into electron-positron pairs? Then there would be a kind of depression in the spectrum of the blazar. And that's not the case in individual spectra, so it would take to average quite a large number of blazar spectra in order to draw out this result. But in the end, we were able to see this blockage. It's stronger for objects at higher redshifts, which is expected. And all are captured quite well by the model, where exactly in such a process photons are eaten away. Why is this important? Because it's a way to know the background of optical and ultraviolet radiation at Z on the order of 1, for example. And if you know the number of these optical and ultraviolet quanta, then you get the data on the overall rate of star formation, for example, at the relevant epoch. Because stars contribute a very large amount of these optical and ultraviolet quanta. Okay. So there are a large number of types of active hydrogalaxies. But here's the thing. Since the early 1990s, they've been trying to describe them in a unified model, and more or less all the main types have been described. There are all sorts of interesting complementarities. What is the idea behind this model? Well, the idea is that you use only a few components. It's a black hole, an accretion disk around it, a dusty torus around the accretion disk, and the jets. And depending on the angle from which you look at this system, you'll see different types of active galactic nuclei. If you're looking directly into the jets, you'll see the blazar. If you're looking in the plane of the disk, you don't see the central source, you'll see a radio galaxy. So you know that there's an active nucleus in the radio galaxy. An active nucleus because the radio emission forms the jets. But you only see this radio emission. If you're looking at intermediate angles, then depending on the level of activity, you either see a quasar or maybe a radio quasar if it doesn't have jets, or a safer galaxy. Accordingly, with the advent of ALMA, there's an opportunity. Not ALMA, I'm sorry. It is DLT interferometric data. With the advent of interferometric observations in the infrared, there was an opportunity in quite a lot of detail on a relatively small scale to study the distribution and properties of matter in the neighborhood of supermassive black holes. This picture is obtained for a galaxy at a distance of 4 megaparsecs. So it's notionally close to galaxies, but you see details much smaller than 1 parsec, as you can see. And so these observational data allow us to test this unified model and study the components associated with dust disks, dust toruses in the center of the galaxy. In general, we can study active galactic nuclei on different scales, not only in the case of our own or some close ones. We can study accretion on the scale of the whole galaxy. That is, there is an inflow of matter into the central part of the galaxy. Then on a rather large scale, in the central flow around the black hole, we can study tori in the broadline region. And finally, in some cases, we can observe the process in the immediate neighborhood of the black hole, where the distance is already conveniently measured in Schwarzschild radii. If in the first picture it's kiloparsec scale, in the second picture it's more like parsecs, then in the third picture it's astronomical units. Depends, of course, on the mass of the black hole. This unified model allows us to build population models for active galactic nuclei. And at the end of this lecture, we will have to get to it. And now let's talk about black hole masses, about methods of determination and some obtained results. There are several methods. They can be related to the observation of the motion of some objects around the black hole. They can be related to the distribution of stars around the black hole, some kind of probing of the black hole's neighborhood. Finally, based on these methods, there are some correlations of how the mass of a black hole is related to galactic parameters. And this allows you to get these correlations between these parameters and allows you to get an estimate. It's not a measurement, it's an estimate of the black hole mass by observing properties of the galaxy that are easier to observe. And accordingly, they can be made in a large number of cases. Accordingly, there are many methods. Here, this picture is taken from the corresponding review. The main ones are listed, but I'm going to go further and say that it is very important to compare methods that are more accurate and less accurate. Perhaps if we're talking about galaxies that aren't too close, like our own or Métis 7, the most accurate methods are the ones that are associated with the maser observations. They give very accurate estimates, and in some cases you can compare estimates made by different methods and calibrate the different methods in that way. And then based on that, you get the relationship between the different parameters. And so you can see that the mass obtained from these correlations correlates quite well with the exact methods. But here at the same time, you can see the level of accuracy. That is, the level of accuracy is not that there is not 10 or 20%, but in most cases it is not even 2 or 3 times. And this estimate is really there on the order of magnitude. That is, we were wrong by less than half an order of magnitude, which is good enough. The main correlations are probably related to the bulge properties. And on this picture, you can see the correlation between the mass of the black hole and the mass of the bulge. And it's really like this, quite good. That is, it covers many orders of magnitude. On the other hand, you can see that there are quite serious bounces. In this case, there are bounces of almost 1.5 orders of magnitude. and the bounces are both to one side and the other. So a mass estimate that's made from expressions like this, it's an estimate, it's just an indication. Well, you can see here, by the way, that the typical mass of a black hole is a very small mass of a galaxy. Even if we're talking about the bulge, we're talking about 0.1% typically. Naturally, this varies a little bit because the relationship is not strictly linear, as you can see, but it's pretty close to linear. There are galaxies that are very much out of this dependence. That's always of interest. Well, here's a prime example. It's the M33 galaxy in the Triangulum. It has a small bulge. But generally speaking, it's supposed to be a black hole with a mass of tens of thousands of solar masses. And you can't see anything like it because it's a close galaxy, visible face on. Everything can be observed very well there in the center. And there are very tight estimates on the upper mass of the black hole. And here's something else that probably needs to be added. A central black hole cannot be any lower mass because there are stellar dynamics. A low mass object will be ejected from the center of the galaxy by dynamical interaction. So you have to have an object in its neighborhood. The object still dominated in mass. Therefore, small galaxies can have small central black holes with masses of thousands of solar masses. But generally speaking, in M33, for example, if we put an object with a mass of 1,000 solar masses at the center, it's very likely that it will eventually move out of the center. Nevertheless, light black holes have been observed. And just on the second slide, the corresponding dwarf galaxy was mentioned. There, as you would expect from a dwarf galaxy, is a small black hole there, and it all fits nicely into the overall correlation. The mass of the black hole is tens of thousands of solar masses, as you can see. The number of measured black hole masses is growing all the time. And it's such a pretty active field. And so the correlations are getting more and more accurate in that sense. There's more measurement data. If you fit everything with a simple step dependence, then accordingly you can pick the coefficients with more precision. And people are constantly trying to look, as the data grows, to look at these correlations, not for all galaxies together, but by breaking them down by type. And yet you can see that even galaxies of different types fit pretty well into roughly the same relationship. But in a very recent paper, people have once again studied the dependence in detail, and they studied them separately for galaxies of early spectral types and for all of them together. But here I have cut out only pictures for galaxies of early spectral types. Accordingly, with what does the mass of a black hole correlate well with such easily observable parameters? It correlates with the velocity dispersion. And it's such a simple step dependence correlation with the velocity dispersion. In a sense, the massive bulge is often derived from this very velocity dispersion. And consequently, it's such a good tool for guessing the mass of a black hole just by measuring the parameters of stellar dynamics in a given galaxy. But again, the errors, as you can see, can be quite large. In recent years, people have become very active in looking for light black holes. Accordingly, they're sometimes called intermediate mass black holes. But this is where it really gets fuzzy boundary, because before we mentioned intermediate mass black holes in the context of ultra-powerful X-ray sources, and there it is a little bit simpler. So there are black hole masses that we can get to with stars. So tens of solar masses, well, maybe small hundreds of solar masses, and there's a significantly more massive object, so thousands of solar masses. So if we're coming from the stellar mass end of black holes, it's already a black hole of intermediate mass. If we're coming from the massive end, it's pretty hard to draw any kind of hard boundary to come up with some physically meaningful boundary to say that 100,000 solar masses or 50,000 solar masses or 257,000 solar masses is the boundary between what we would call intermediate mass black holes and supermassive black holes. So it's a pretty arbitrary thing. Well, here's the relevant article people, including again from the Geisch, tried to look for intermediate mass black holes from spectral data on galaxies and found quite a few objects. with masses in the tens of thousands of solar masses. The masses here are in the thousands of solar masses. Accordingly, the green stars are the new candidates, and the black stars are the new candidates obtained in this work. Apparently, this direction will develop, that is, the number of objects with smaller masses will grow. And this is one of the reasons why this gap between stellar mass black holes and really supermassive black holes will be filled. But this is not the only reason. We will also talk about the second one, but more likely at the next lecture on dwarf galaxies with black holes. There was a good review 3 years ago. On the one hand, it is before this paper, but the number of new candidates is growing, and this is good. But here's this very informative review, where I've just taken some beautiful pictures. Up until recently, I honestly haven't checked the record now. I didn't come across any substantial articles on the subject. One of the most surprising combinations in some ways was this one. In this case, we're talking about a really massive black hole, and the galaxy itself is a dwarf galaxy. So the galaxy, here it is zoomed out. So there are big, beautiful galaxies. There's this formation here. It's zoomed out, and it's very small indeed, but it's got what appears to be a massive black hole sitting there, which is quite interesting. This is most likely due to the fact that the outer parts of this galaxy have been stripped away as a result of the interaction, for example. So in general, usually when we see a black hole that's too massive for that galaxy, the first thing that comes to mind is that they were once more or less in harmony, but then the galaxy was ripped off by the interaction. But in general, anything that bounces off typical parameters, typical correlations is quite interesting. In general, statistics is constantly growing on low-mass black holes in galaxies. But in this paper, they go up to hundreds of solar masses in the case of dwarf galaxies, which is really interesting for reasons that will be introduced in the next lecture. The lightest black holes may be of some very specific interest related to the origin of supermassive black holes in general. Well, here is another massive black hole in a dwarf galaxy. I will not dwell on it. And this is an interesting subject in its own right, and it can be tested in observation. That is, the data on massive black holes in small galaxies in this case were compared with modeling data in the Eagle package. And so accordingly, what's bouncing back a lot is due to tidal stripping of galaxies. A completely separate issue is black holes in globular clusters. I put it here simply because black holes are usually... If people talk about finding black holes in globular clusters, they're talking about masses of thousands, tens of thousands of solar masses. The difference between globular clusters and even dwarf galaxies is pretty fundamental, apparently. Globular clusters are what was formed in the galaxy when it formed. That is, these are structures that are initially, generally speaking, gaseous. They are not dominated by dark matter. The galaxy is normally a dark matter-dominated structure, but that's why they would have different histories, and it's still not clear how common, how typical black holes should be in globular clusters. Once upon a time, in the early days of X-ray astronomy, this was the standard idea because they started to find X-ray sources in globular clusters. The angular resolution 50 years ago was poor with X-ray telescopes, and one of the ideas was that it was the black hole in the center of the cluster that was emitting, and people were building models where you could get holes like that. But then they were able to show that the sources are not central, that it's just a collection of a large number of double systems. You remember that binary systems with accreting neutron stars with low mass companions in globular clusters are often caused by spillover capture, because of dynamical capture, because of interactions. And the X-ray arguments in favor of black holes in globular clusters have more or less all dissipated practically. And so new candidates are emerging from the other side. These could be radio observations, which you and I mentioned when we talked about single black holes, or it could be just observations of stellar dynamics. So, for example, you can measure pulsars, in globular clusters, there are many millisecond pulsars for the same reason that you can measure many low-mass X-ray twins. So accordingly, by studying the pulsar population, you can measure the acceleration of these objects because you have very good timing, and you can see what potential describes the behavior of these pulsars. And very often it's not just this kind of smoothed cluster potential, but a potential that has a central massive object in it. Accordingly, here is one of the latest results from a few months ago on the globular cluster M62, just a pulsar. On the other hand, there's been some work recently again where people have been studying the stellar dynamics in globular clusters and vice versa. They say that the data is more consistent with the absence of black holes in the two globular clusters Omega Centauri and NGC 6624, which were considered very good candidates for central black hole clusters. The idea is that if you have a central black hole, in all likelihood you make some of the stars move at very high velocity ejected. So if Omega Centauri had a central black hole of 47,500 solar masses, as many calculations have shown, then this dotted line here says that there would be stars with speeds greater than 50 kilometers per second, lots of them. And they're observed by more than one. For more than 61 is observed. And the authors believe that this is a problem and therefore point out that there's no such massive black hole out there. And they can describe the motion data of ordinary stars perfectly well without a black hole at the center of the cluster. But again, there remains an ambiguity here. There are dwarf galaxies combined in this picture, a special type of galaxy, compact galaxies, globular clusters, similar objects. And you can see here, for example, the globular clusters for Omega Centauri, these 47,000 solar masses, that's what's marked here. And if you think that there are black holes, they fit nicely into the general correlation with the mass of the objects themselves. So in that sense, globular clusters are bigger themselves. From Radio Horizon, people have tried to look for accreting black holes of intermediate masses in globular clusters. You remember that if we have an accreting black hole, we almost always get jets. And jets almost always mean radio emission. So there's a relationship between radius luminosity and X-ray luminosity, which is well established, for example, for X-ray doubles. But in this case, only upper limits were obtained. Nothing has been recorded, and this is seen as an argument, well, at least against accreting black holes. Another thing is that they may not accrete matter with sufficient efficiency simply. And finally, this is, I think, the last slide on globular clusters. There was a very beautiful result a couple of years ago. People apparently observed a tidal rupture of a star in an extragalactic globular cluster. That is, a transient was observed that was well localized in a globular cluster in one of the not very distant galaxies. And if so, then there must be a black hole with a mass of tens of thousands of solar masses in this cluster, and it could give the appropriate signal associated with the tidal rupture of a star that came too close. Maybe with the advent of good X-ray surveys of the sky, i.e. with Rosita, people will identify more such events, and that would be very interesting. Everything with globular clusters, but not everything with black holes of intermediate masses. There's a very interesting hypothesis, but I'll emphasize the word hypothesis again, that intermediate mass black holes have been observed in the vicinity of Sagittarius A star. This fits nicely into the scenario we will discuss in the next lecture. The idea behind the search is as follows. People are observing compact gas clouds traveling at very high speeds. The idea is that some of these formations, they're so compact precisely because there's a massive object sitting in the center, which is a black hole. And the central part of our galaxy, it's very well studied. In particular, there are several of these clouds that are known. And in this recent paper, the people who are developing this field, they've presented another candidate. This is the fifth candidate for intermediate mass black holes in the galactic center. Okay, now on to all sorts of unusual supermassive black holes. Just a reminder, we're discussing masses now. We'll continue to discuss other methods of determining masses later on. But let's say we have the masses determined. So what could be so unusual about this? Well, it would seem that the unusual thing would be a very large black hole mass, but that's not always the case. The current record, apparently, is an estimate of the mass of a black hole in this galaxy here. 40 billion solar masses is a lot. That's close to the limit. Well, the limit is so vague, but you and I will discuss where it comes from. To get to, say, 100 billion solar masses is insanely difficult. It's very hard to get that much gas into a black hole. There are processes that prevent that from happening. But in this case, a massive black hole is a very massive galaxy. It's the brightest galaxy in a large cluster. And it's in galaxies like this that the most massive black holes are observed. And you can see that on many correlations, this black hole fits very well, as is customary. The object of the paper is shown in red, so it's easy to pick out. Accordingly, it can be seen that it does not bounce much off some of the other objects, bounces from the correlation with velocity dispersion, for example. And it doesn't bounce out of that correlation very much. So sometimes objects that seem to have record parameters are not a big problem. And on the contrary, very light objects can be a problem. So there's a black hole detected by X-ray data. So there's an active nucleus. We have an estimate of the mass of the black hole. At the very least, at least the Eddington limit can be used. At least we're talking about tens of thousands of solar masses. But in this galaxy, there are no bulge at all. So it would seem that on the correlation, it should have a 0. And there's a black hole. And that is a problem in its own way. Another example of such an overly massive black hole. Here's a related object. There's a very large bounce from the correlation here. But however, if you look at the edge of the tendril here, it sits, the bounce is smaller, but it's still quite large. Accordingly, maybe we should have somehow stripped this galaxy or something else to do with it, but there are no obvious traces of this, by the way. A separate problem is very massive black holes at large redshifts. We will talk about this next time. The problem here is how to get them formed in time. That is, to get a galaxy, a newborn galaxy, with some black hole in the center, it is not difficult. It's hard to get a lot of mass, if only because there's also the Eddington luminosity. You can't put very much gas in there. And dark matter, as you remember, doesn't flow well into a black hole. It doesn't cool down very well. So basically, the black hole is fueled, of course, by regular. And if matter flows into the black hole at a high rate, an accretion disk is bound to form. Energy starts to be released there. And the first thing you can run into is the Eddington limit. And even if you drive the black hole in the Eddington scenario at the maximum possible accretion rate, it's fantastically difficult to get to 11 billion solar masses by Z5, and that's a big problem. Sometimes the problem can be solved, but in this case, a massive black hole is observed in a galaxy with massive star formation, and over time, the stellar mass of the galaxy will grow. So on this plane, the object will move towards normal. The black hole won't grow much anymore. But the stellar mass of the galaxy will grow a lot. And so the black hole will eventually, over billions of years, it won't look like a typical black hole anymore. That is, strictly speaking, it means that now it looks somewhere quite typical. Accordingly, here's the topic. Calculating the combined change in mass of a black hole and the mass of a galaxy. It's actively developing. In part because there are new observational data that can characterize the rate of star formation. And so we can build scenarios in which we will calculate how the black hole mass and the stellar mass of the galaxy will change with time, and try to reproduce what we see in our neighborhood from what we see at large redshifts. There are all sorts of other correlations other than the ones we've already discussed. For example, the mass of a black hole with the absolute stellar magnitude of the bulge. It's not quite the same as stellar mass because stars evolve, and that's quite important. Accordingly, you have a process of star formation, and the bulge is growing. And so the absolute stellar mass, the absolute stellar magnitude grows modulo the absolute stellar mass. The mass of the black hole grows, but then the stellar population of the bulge ages, and so its luminosity decreases. So if we see a galaxy somewhere far, far away with a very bright bulge, with a bulge of very high luminosity, then by Z0 that galaxy will be much more ordinary in that sense. And the existing correlation established at low redshifts can be reproduced in this way. Accordingly, correlations for active galaxy nuclei are sometimes studied separately, i.e. the breakdown is not by galaxy type, but by activity, and within that you can develop them by galaxy type. Accordingly, there is a lot of work with galaxies of early spectral types, but I probably won't dwell on that. We will talk about it for too long. It's interesting, it's such a fresh result that new data shows that the correlation between the mass of a black hole and the stellar mass of the galaxy does not evolve much with redshift. Here, though, it seems like the sample isn't big enough yet, and perhaps we should wait until there are hundreds of objects like the sample. But nevertheless, the result is already interesting. People start at Z2, and accordingly, looking from a cosmological point of view, this is a very important, very big stage of evolution, from Z2.5 to Z07 approximately, which is where the main sample is. And yet this is more or less in line with what is observed at low redshifts, that is, has been done in other work by other authors, by Rains and Marta Volonteri respectively, all of which suggest that evolution is not very visible, that to a somewhat surprising in the context of some evolutionary scenarios. Okay, back to mass estimation methods. I already mentioned the mass methods. They're some of the most accurate for distant galaxies. The idea is that if you observe a maser, you observe a very narrow spectral line. And if that object is orbiting a central black hole, you can determine the mass inside the orbit of maser. Naturally, something else is swept in besides the black hole, but we are talking about very small scales, tenths of a parsec, so you can't put a lot of stars or anything else in there. So if you get a mass on the order of tens of millions of mass of the sun or more, that mass is dominated by the black hole, so the black hole is the main contributor, and the maser methods at distances of tens of millions of light years are the most accurate, because we can't see the motions of individual stars at those distances. Accordingly, there's an ever-increasing number of objects for which maser measurements have been made, and people are trying to see how these measurements correlate with correlations established by other methods. And in this case, the red dashed line is the correlation between mass and velocity dispersion for elliptical galaxies. Well, you can see that some objects fit here very well and some objects don't fit very well, which further characterizes the dispersion that we've been discussing. Well, the bounce here you see is less than an order of magnitude in mass. This in general, not so bad, I would say. It characterizes the accuracy of the corresponding correlations. For close galaxies, for relatively close galaxies at megaparsec distances, a little bit more than that, we can study the kinematics of the gas. And that was the method used for the MATE-7. That is, for a long time, it was the primary method for determining the mass of the black hole in question. And by this method, a value of 3 billion solar masses was obtained, but with an accuracy of 2. This corresponds to what was obtained by the Event Horizon Telescope, that is, compared to more accurate data. Gas kinematics from multiple galaxies works. Well, for many here, actually the upper limits, which is not so interesting. And where there are not upper limits but precise measurements, you get, by the way, quite close to what you get with the other method, the method of reverberation mapping, which we'll talk about later. Gas can be used in another tricky way. If you observe a hot gas and you think it's in equilibrium to the corresponding gravitational potential, then the temperature of the gas corresponds to the depth of the gravitational potential. If you think that the gravitational potential is set mainly by the black hole, then you can get an appropriate estimate of the mass. And this has been done for the galaxy NGC 4649 and was obtained an estimate of the mass of the black hole. Not only does the gas naturally line up with the gravitational potential, the stars do as well. And ideally, by observing just the stellar density, which you can do for quite distant objects now, you can again get the mass of a black hole. Well, there are these theoretical stellar density profiles are plotted. Naturally, when you go under 1/10 of a parsec, you have the gravitational potential being determined precisely by the supermassive black hole, if it's there, and then you can get an accurate estimate of the mass. This method often fails. Well, here we are going to talk in particular about double black holes. Naturally, if you have a double black hole at the center of the galaxy, it washes out this sharp peak, this sharp cascade, which is created in the stellar density distribution by the presence of a massive object. Another very exotic method was applied 2 years ago to a mapped galaxy, which is a gravitational lens. By analyzing the fine details in the lensed image of a distant galaxy, of a more distant galaxy, the authors found that some of the details can be well described if the lens has a rather complex potential, where in particular there is a point massive object. So some of the details are related to the lensing on the central supermassive black hole and a corresponding mass estimate of about 10 billion masses of the sun. Finally, the already mentioned reverberation mapping method. It is not very accurate, but it is good in that it can be used for a large number of galaxies. Let me just turn to the picture, I guess, and then go back to the previous slide. The idea is this. We have a supermassive black hole and we have an accretion disk around it. And there is radiation, we can identify it, that is formed in this disk. We know from a huge number of objects that disks don't shine all the time. They're variable. Something happens there, the accretion rate changes. So we're going to see, for example, ideally a flash related to the behavior of this disk. And so we take the radiation directly, we can pick it out, we can identify it, and we can see that flash. Some of the radiation from this disk spreads out and falls into what we call the broad spectral region. Here there are clouds of gas that re-emit the radiation from the central source, from the disk that hit them. And so therefore, if we've had a flash here, then with some delay, we'll get a flash here because there's a delay. You're determining the distance from here to here. Well, conditionally speaking, if the delay there is a day, then the distance from here to here is a light day. And then from the spectral lines themselves, we can determine the velocity of these gas clouds in the gravitational potential. But at these distances, it's already determined by the central black hole. It's a simple problem. So if we neglect the details, you have the distance at which the object is traveling and you have its orbital velocity. If you assume a circular orbit, you immediately get the mass of the central object. That remains the only unknown parameter. There are actually many unknown parameters. There are orbital parameters, all sorts of projection effects. But fortunately, there are a lot of these clouds. And so you can get spectral line data from different clouds and get a more or less complete picture. This is the kind of thing has been around for quite a long time. And it wasn't originally invented for this purpose at all. But it's been used for almost half a century for active galactic nuclei. And again, it's a pretty good thing that this method is still pretty massive. So compared to stellar kinematics, gas kinematics, masers, You can measure more galaxies with this method. And so it contributes a lot to the overall statistics, but it's important to calibrate it. And a few years ago, a rather interesting result was obtained for one of the galaxies. Naturally, the unknown parameter is the distance to the galaxy, and knowing of the distance helps to determine the mass of the central black hole. For example, if you use the estimate from mass sources, and there were flares in the galaxy in question, and we can separately separate the radiation from the central object. This radiation is shorter wavelength radiation, and the radiation that's being re-radiated by the dusty structure around it. So again, we have the delay that we know, and for the dusty structure, by direct measurement, we can determine its angular size. And accordingly, you have the angular size, you have the size determined by the signal delay, that is the size in light seconds, conditionally speaking. Accordingly, you directly determine the distance from here. By the way, this galaxy is used as a calibration galaxy. And so that's why, and so changing the distance to this galaxy, that the masses of many black holes had to be reevaluated at the same time, that the calibration was used to determine. Well, I finally got to the last part of the lecture, population synthesis of active galactic nuclei. Population synthesis, as you remember, is a rather powerful technique used in astrophysics. And in this case, we're interested in evolutionary population synthesis just as we were before. Although, in some sense, we can also talk about empirical population synthesis for active galactic nuclei, but this is such a separate topic. Here's a picture that we'll be discussing next time more. It's very important because there's a question of where supermassive black holes come from, how they evolve, how their evolution is related to the evolution of galaxies. And the idea is that at large redshifts, the big ones are there, 10, 20, 30 maybe. Germinal black holes form. There are several channels for their formation we will discuss. They can be black holes with masses of hundreds of solar masses if they are formed from the first stars. There can be black holes with masses up to hundreds of thousands of solar masses if they are formed. Due to the direct collapse of gas clouds, there could be anything in the middle, and in the process of galaxies forming, black holes get inside these objects, get to the center, of course, because they're massive. And then their mass starts to grow due to accretion, due to merging with each other, and all this can be modeled. But the important thing is that in this process, there are constantly ejected black holes, and they will just have an intermediate mass. So this is the main reason why, in principle, this gap between stellar mass black holes and supermassive black holes should be seeded, because there's a large number of objects that are not in double systems, that don't sit in the centers of galaxies. They exist to some extent on their own, but we'll talk about them next time. And in this picture, you can create specific scenarios for the growth of black hole masses, changes in the rate of accretion on them. That is, accordingly, you model how you have active nuclei of galaxies of different types appearing and disappearing. And people are actively engaged in this simply because the sample is constantly growing. The amount of data on active galactic nuclei is constantly growing. So here's a picture from population synthesis relatively recently. Accordingly, on the vertical axis is the mass. On the horizontal axis is the ratio of the luminosity of the active galactic nucleus to the luminosity of the galaxy. This is the unit line. So right here on the right side, you have the active nucleus emitting more than the whole galaxy together in the mirror. It's not. This is where the quasars sit. That's where more or less normal galaxies sit. They have higher, lower accretion rates of accretion, and accordingly there will be more or less luminosity. And all this is compared to the result of population calculations, because it's always interesting to see what else we'll see. This particular work solved one of the problems of population synthesis. Remember, you and I discussed them. Here they were trying to make specific predictions for the James Webb Telescope, that it would be able to see what important steps in the evolution of galaxies and the evolution of central black holes they could thus to test. The X-ray background is made up mostly of the huge number of unresolved active galactic nuclei. And accordingly, the population modeling and evolution of active galactic nuclei can be compared to the X-ray background data. In a related paper, just such a comparison was made. Here it is just the flux distribution, and here it is the redshift distribution. But you can see that people are able to fit the X-ray background with very high accuracy, with such surprisingly high accuracy, I would say. But that means that at least you can make models of the evolution of active galactic nuclei that look like to what's actually happening. Here, accordingly, we've been calculating the evolution of the populations of active galactic nuclei at redshift, so different curves drawn for different redshifts. And you can see, accordingly, evolution. One can see the change in the number of observables. It is very important here that the number of objects for a flux greater than a given flux is shown. And accordingly, for the most part, the observational data at the moment is dominated by objects that are at small redshifts, that is at redshifts less than 1. Nevertheless, there is also a noticeable number of galaxies with redshifts up to 5. It's very important to take spectra into account for modeling active galaxy nuclei. Galactic nuclei, naturally, the spectrum is one of the parameters. And by comparing the modeling data with observations, you can get the spectrum. So you can infer not small details, but large structural details, the spectra of distant galaxies. And the role of compositing in shaping those spectra, which is also quite interesting. Finally, evolutionary synthesis of active galactic nuclei can be combined with modeling of large-scale structure. I have already mentioned EAGLE. Its competitor is the Illustris project, which is evolving and in its new incarnation is called slightly differently. TNG has been added to the name. Accordingly, this thing calculates how your large-scale structure is going on, up to the formation of galaxies, up to the evolution of those galaxies, taking into account the behavior of the baryonic matter. And so the model has the ability to calculate star formation and then supernovae and their inverse effect on the interstellar medium in this galaxy. And in particular, it is possible to calculate, supplementing this program, it is possible to calculate the behavior of black holes. That is, you can calculate the rate of gas influx, which on the one hand determines how the mass of the black hole will grow, and on the other hand, determines the accretionary luminosity of the black hole. And this is done actively, not only using Illustris, I just chose the appropriate article and pictures to show it, but also with other packages. Accordingly, you can even separately look at the statistics of such synthesized black holes in galaxies of different types to see how you form a correlation between the mass of the central black hole and the stellar mass of the galaxy. Which of course is interesting, which of course allows you to additionally, including the ability to additionally test galaxy formation models where there's still quite a lot of uncertainty. So all of this allows us to calculate the evolution of the accretion rate on black holes. I probably won't dwell on this any longer, but the basic idea is that, as you can see from the left picture, different curves correspond to different multiple shifts of the accretion rate distribution, which is expressed in Eddington units. That is the Eddington rate, 100th, 1/10,000th of an Eddington. You can see that the further back in time, the more black hole galaxies there are, and not in absolute numbers, but relatively. You remember that the maximum is still on the Z2, right? But here we are talking about a fraction, not an absolute value. And so accordingly, in the first billion years of the universe, black holes, if they accreted, they were often accreted at a rate close to the Eddington rate. And as cosmic evolution proceeded, this shifted. And currently, the typical accretion rate is about 1,000th of the Eddingtonian rate. Accordingly, all of these models can be tested in the near future when there's more data on active galactic nuclei at very large redshifts. This prospect is linked to the emergence of new instruments. They are listed here. The Athena X-ray Observatory, the very large European telescope James Webb, the Spica Space Project, ALMA is already operational. I mean, of all of these, only ALMA is working at the moment. Finally, in the radio band, ESKI. So we can hope that, of course, the amount of data on supermassive black holes will continue to grow for a long time to come. And since there are many unsolved problems in this field, then accordingly for the next 10 to 20 years, the field is provided with such a clear prospect of development.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.